So very good afternoon to everyone. So I am Rohit Gehlot, basically the TA for this material characterization course. And so today is the first session of the week one. So firstly, if you have any expectation from this, what I can say, like this tutorial, like what you want to include or what you want to cover, like you can let me know by my mail ID. So I will be sharing my mail ID in the chat box. So like whichever concept you are not getting in the subsequent lectures, or like you have some doubts, please let me know by this mail ID. So as today is the first session, so it will be a brief one. Like it will only be solving problems, and some of the problems will be solved from the next week. Like whatever doubt you have, or or some specific topic you want to recover, please let me know by my mail ID. So I will be one second. Yeah, so I was saying that uh, like uh, from the next week, whatever like doubts or questions you have, please let me know beforehand. So like I will be focusing majorly on that. So it will be good for like everyone. Uh, and besides this, if anyone has like any other expectations from this course, please let me know now. So from the next week I will be preparing accordingly to that, because this session is mostly for discussion and for solving problems. So that by that way, like it will become a more interactive session, so it will be beneficial for both of us. So if besides this, if anyone has any other expectations, or like someone wants to share his or her thoughts, please do now. So we'll wait for 5 more minutes to let some other people join, and then after that we will start the today's session. Okay. Meanwhile, if anyone has anything in their mind, they're free to share it. Yeah.
Hello, sir.
Yeah. Hello. Yeah.
Yeah, actually, yesterday I have joined for the session late, so I have missed the things what have been discussed in the previous problem session.
Okay.
When can we have that recordings of those sessions, sir?
Yeah. So generally, like before the next week's Tuesday, like the link for that recorded session will also be shared, because all these problem solving lessons are generally recorded and then uploaded on YouTube. So the link will be shared soon. So no issues regarding that. Okay.
Okay, thank you.
Okay. Okay. So let's start the today's session. So again, I will like introduce myself. So I'm Rohit Galut, and I am the TA for this materials characterization course. So as today is the first session, so it will be a brief one again. So and generally like in these problem solving sessions, we will be solving some problems, and also like if you have any doubts, please mail me as I have shared mail ID also in the chat box. So firstly, let's start with the uh, what uh, what was then basically covered in these in 1 second. Okay. So in the week one, like generally the fundamentals of optics were covered by Professor Sankaran. So generally basics of like how to perceive or like firstly, the major concept was covered as the like to perceive or image a structural feature like the lambda of your probing radiation should be around your size of the feature, and resolution is a function of lambda, and also uh, he explained or like taught about the dual nature of light, and then the different about the basics about the electromagnetic waves, and then the rules of the simple lens like then the concept of magnification he also taught, and also then basics of diffraction and interference uh, were also were also being taught by him. So as seen in the figure also like the light is an electromagnetic radiation and have properties of both waves and particles. So he explained in depth like this concept, and like how to see the wave nature and then the particle nature also were clearly to him. So please visit those videos also, and also after that like here as it can be seen that the different like as your like the wavelength of different gamma rays, x-rays, uv, infrared, and your visible light also here is shown here. And then after that he also taught about the Rayleigh criteria for your spatial resolution, concepts of numerical aperture, and then some other concepts like image brightness, depth of field, and depth of field were also being taught by him. Then there's some lenses defects in it. He also taught about the lens defects, and so let's start with the some basics of these. Like I think the majorly all the videos you have already been watched, so it is more or less a solving session only. So still, but if you see about the diffraction, like it is a scattering of light by an object into the divergent waves, or it can be like it is the spreading of light that occurs when beam of light interacts with an object. So similarly, if you talk about the interference, so it is the recombination and summation of two or more superimposed wave, and its manifestation of the same processes like so electromagnetic interaction with your matter like involves like reflection, diffraction, and refraction and others. It is part of scattering phenomena only. All of these are like been taught by in the lectures only. So these are not the prime aim of this lecture. We will be solving some of the problems only. So let's start with the problem number one, which tells about like which of the following condition is required or necessarily for a collimated waves. Like the options are the coaxial path of the propagation through space, same wavelength, same phase, the same state of the polarization. So like these problems will be like more or less related with your assignments, or the quizzes which have been shared. So if we will solve these second a moment. So if these problems have been are been solved, then like then one can easily solve the assignment problems as they have the marks in the final marking also. So let's so if anyone is like if anyone can tell about what will be the answer for the first one, like which of the following condition or required necessarily for the collimated waves. So the
I
collimated
think
wave
it will be coaxial paths of propagation through
space, yeah, right, yeah. So the first one has the A is the corrected answer. Like for the collimated waves, like they propagate in the same direction or like without convergence, like without convergence or a divergence. So the coaxial path of propagation through space is the correct answer. And also these are the parallel rays. The collimated waves are the parallel rays, and they spread minimally as they propagate in the direction. Now, if we move to the second problem, like in light microscope, the ray subtending angle on the dry objection lens is 39 degree, and then we want to increase the resolution of the microscope. Which of the following option is best suitable? So, so here the concept of the basically the numerical aperture comes. So, if anyone would like to like share his or her thoughts, please do so.
I think C will be better. Medium between objective lens and specimen filled with oil.
Yeah, right. C is the right answer. So I will explain it also in some elaborative manner. Okay. Uh, so if you talk about the numerical aperture, uh, so numerical aperture is the ability to gather light and resolve fine specimen details. Okay. So as it has already been covered in the lectures, and the if we talk about uh, the for dry lenses, like here as the problem says that for dry objects, one second. For the dry objection lens, yeah, so for the dry lenses the numerical aperture is limited, like after like as the ray subtending angle increases to 41 degree, it causes the total internal reflection because because the angle is more than its critical angle, so total internal reflection happens. So so that's why to increase the resolution, the some media is better to add, like if we write it that in that manner. So if we so as we know that the numerical aperture can be written in the form of n sine theta, and where n is the refractive index. Sorry, today I don't have the cursor, so next time I will be having the properly. So this is the refractive index between your objective lens and your object, and generally and for air it is around 1. Okay, it can be like also written as the range of angles over which your system can accept or emit light, right? So if you talk about your aperture in simple language, it can be understood as the opening through which your light passes to enter the camera of your okay. And then it, aperture is explained by your f number, which is your ratio of your focal length to your diameter of your aperture. So smaller is your f number, the larger will be your aperture, right? And similarly, if the larger is your f number, the smaller is will be your aperture. So this concept will be more explained in the following like problems. Still, I wanted to convey that the C is the right answer, like the media between, because it will enhance your refractive index, and that's why your numerical aperture will be affected, and which will be directly affecting your resolution also. Okay, so like moving to the third problem, like the range of position for an object for which the image sharpness does not change is known as. So this is the basic definition of the. Anyone who would like to say the answer? Yeah. So the range of position for an object, like for which your image sharpness does not change, is known as your depth of field. Okay. Okay. So your so there is like two terms of like depth of field and your depth of focus. Okay. So majorly the difference has already been well taught in the lectures. Uh, so if you talk about the depth of focus, it is the thickness of your image within which the total image is in focus. Okay, and then if you talk about the depth of field, like the distance with which you can move your object, still the image remains in the focus. So and similarly here the relay criteria also comes. uh, I think you have already watched the video where uh, it was taught that around lambda by 4 distance and that the for the depth of field formula was derived and all. So I think it's already been covered. So now if we see the fourth problem here, for a yellow light which is and having its lambda as 580 nanometer, and then your five source optical microscope having medium between objective lens and specimen filled with a cedar wood oil with a refractive index of 1.5 and the subtending angle is 39 degree. Find the depth of field is of that. We also try to solve this. After that we will be covering a small concept and solving this. So try to solve this problem, like what will be the answer for that. So meanwhile I will write something like the relation between your aperture and your depth of field. So like when your aperture is larger, like smaller is your f number, so it will result in your larger aperture, this larger aperture opening and greater amount of light will be entering through your camera. So when wide open, so when your aperture is wide open, so more light will converge to form the image, like on your camera sensor. This this will increase your convergence of light, and it will allow a shallower depth of field. So like sometimes, like in your MCQs, it may be asked like what is the relation between this your aperture and your depth of field. And also, by shallower depth of field, I mean only a small range of your distances in your will be in sharp focus, while objects in front or behind that range will appear blurry or out of focus. Okay, so I can like I can say when more of your like object needs to like focus, like if you want a better focus, a smaller aperture, like while if you want, when you want to isolate your subject from your background, then the larger aperture is preferred. So that's how the cameramans are like play with this aperture size while taking the pictures. This is a very important concept, so one should know about like the relation between your what will be the relation between your aperture and depth of field and your resolution, like how it will be affecting. So if anyone has solved the problem for they can tell me like what is the correct answer for that.
Let's see.
Yeah, C is the right answer. Yeah. So the formula for that is already been derived. So uh, one should visit and see one second. So depth of field is for this problem is can be calculated by the formula of n lambda by your numerical aperture square. So I will suggest all of you like to see the Rayleigh criteria, like how it was derived. So I won't be deriving it here, but one should know like how this formula came. So from the definition of depth of field, we know that if it like suppose this is the point P2 and this is the point P1. So this is the minimum distance, or the maximum distance by which your object can be moved and without any effect on your resolution. And suppose this is the where your image was forming. So by simple trigonometry, like there can be a correlation can be made, uh, and then your depth of field can be calculated. So you also try to come to this formula and then if we can, then it is simple, uh, like in the problem lambda is given, and then your n is also given, and then the angle is given as a 39 degree. So one can easily solve this. I think this is also in this week's assignment also. I think some values are different only, so you can also go and check if you have corrected, if you have marked the correct answer. So now if we move to the next problem, which of the lens defect occurs when light is non-monochromatic. So this was also been taught in a depth, like there are different defects like chromatic aberration, spherical aberration, coma, astigmatism. Besides these also there are some other defects also. So as this problem comprises only these four defects, so I have summarized their description, causes and types also, and then how they can be corrected. So if you talk about your spherical aberration, so spherical aberration will cause your different portion of a lens to focus light at different points, which will result in your blurring and reduced image sharpness. Generally, the cause of this is that when your light is passing through the periphery of an image, sorry, periphery of a lens is focused differently than your light passing through the center. So similarly, the different defects are also being summarized. So if anyone has if anyone can tell from this writing and also from the options, which will be the correct answer for the question number 5.
Chromatic aberration.
Yeah, yeah, right. So chromatic aberration will be the correct answer. So as the question was, which of the lens defect occur when your light is non-monochromatic? Sorry. So this chromatic aberration occurs when different wavelengths of light are reflected at by different amounts, which will be leading to color fringing around the edges in your image. Okay, so basically it is the inability to bring all the colors to a common focus point due to the dispersion of light. So the more can be the in-depth knowledge can be from the lectures by Professor Shankar. So you advise, if anyone who hasn't watched these videos, he or she should watch those videos. Okay. So now if we move to the problem number 6, for an optical microscope, the focal length of an objective lens is 40 mm, and then the focal length of your eyepiece is 10 mm, and the optical tube length is 200 mm. Find the total magnification if the distance of your distinct vision is 100 mm. Now, this is also a simple problem. So try solving this and please let me know the answer. So the total magnification can be calculated by the multiplication of the your M0 magnification and magnification of the eyepiece also. So this has also been in the uh, lecture video also. So
Sir, option D.
D.
yeah, 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 right. So option D is the correct answer. So this can be calculated as your multiplication of your M0 to M. Then this can be simplified as I think the calculation can be carried out. Yeah. So now moving to the problem number 7. So we need to calculate the optical path length difference. So this problem was added uh, to show the importance of this parameter, which is the optical path length difference. So the optical path length difference for a ray of light passing through a medium is given by the multiplication or the product of your refractive index to the distance that product or the light has traveled in that particular media. And then if we talk about the difference, it will tell about the optical path length will tell about the behavior of your light passing through different media, and generally the importance of that is in the it is important in the context of interference. So the optical path length difference is also crucial in your phase difference calculation for two interfering waves. So basically it is important in your analysis of interference pattern, diffraction effects, etc. So this is also So this is just to this problem was just added to show the significance of this term, the optical path length difference. So try solving this, like what will be the value for your optical path length difference. Yeah, 0.255 is the correct answer. Please mention the unit of that also, like what will be the unit 0.255. So this is so this can be calculated as simply, and then this is your product of your refractive index and the distance, like there are two medias. One is having the refractive index of 1.5, another is having your 1.33, right? So if we talk about the optical path length difference, so the distance is, like, if we assume it as same, so we can write it as, so simply we can calculate. This will come around 0.255, as someone has correctly wrote in the chat box, like it will be around 0.255. The unit has to be mentioned, so it is in micrometer only, because the unit of T is here is 1.5 micrometer only. Okay, so moving to the another problem, which is the same as that, the defects. So tell the name of the defect when the image plane is not flat but it has a concave spherical surface as seen from the objective lens. So the correct answer, I have mentioned the answer with it also. So the correct answer is the curvature of field. If we talk about the curvature of field, it causes the plane of best focus to be curved instead of flat, right? So when the lens is focused on the central portion of the image, the edges or corners may be out of focus and vice versa. And majorly the cause of this is from due to the lens design, and particularly in lenses with wider aperture or specific optical characteristics. Okay, it may be more pronounced in wide angle lenses and fast prime lenses. Okay, so the correct answer is the curvature of field. So the next problem is which light would prefer better resolution, and explain with the reason why. Anyone who would like to attempt this? Yeah. So this was the first video of the Professor Shankaran, and then the first line was itself that to perceive an image, the structural feature, to perceive an image or the structural feature, or the lambda of your probing. So a probe should be around equal to your the site or feature which you want to uh, see in your imaging and all. So this is, I think, the most important. Second. Yeah. So from that concept only, the problem 9 can be solved, like which light or which which light would prefer better resolution. So among blue, yellow, red, and green, which one has the shortest wavelength?
Blue.
Yeah, blue is the right answer. So as the concept is that the shortest wavelength of the visible light, whichever it is, will be having the giving the maximum resolution, and the blue light, which is having around 500 nanometer, as the shortest wavelength compared to yellow, red, and green. So obviously it will be having the better resolution. So the concept is very important that the resolution is a function of lambda. So that should be like written in mind, and then we can solve this problem here. So now, to form an image, the minimum number of diffracted beam required to enter in objective lens. So this comes from the base criteria, and then for a lens to form an image, at least two diffracted beams should enter the objective lens and allowed to recombine in the image plane. Yeah. So this is also been covered in the basics of the week one. Now, if we move to the next problem, like the best resolution for an optical microscope is about. Anyone who would like to comment on this?
0.1 micron.
This is not the correct answer. So basically the correct answer is around 200 nanometer. So, and also can read about the resolution for different elements, different like I think in the subsequent lectures the SEM and also will be covered. So it will be better to take at that lecture, like week 2 or week 3 only. So the best resolution for optical microscope is around 200 nanometers. Similarly for SEM, different SEMs, TEM, and also will be covered in the subsequent lectures. Like then we will discuss this more. So the coming to the next problem, so the figure shows a graph of V against you. So determine the focal length of your lens. So uh, try solving this problem. Anyone would like to? Anyone solved this? So this problem can be this problem is also a very simple problem. So if we write like if we see that at this line v is equal to your u, so if you will replace it like so suppose I have like at firstly like suppose if I take v as u, so I can write your u is 2f. Similarly I can write v also as 2f. So at this line all the coordinates like and abscissa and x and y coordinates are 2f comma 2f. Multiplication of these 2f comma 2f. So like so if I take like this point with 30 and 30 are equal, like the intersection point of your v and u and this curve is this 30 and 30, right? So if I take this, then if I put it as equal to 30, because all these points are showing as 2f, so the focal length is around 15 centimeter. Okay, so these were the problems I wanted to like cover in this week. So as week one is that's the starting of this course, so that's why this lecture was a bit short. From the next week, dedicated lectures will be taken for around 2 hours. So if anyone has any doubts regarding the week one or any suggestion for like what I should cover in the week second, please let's discuss. So it will be beneficial for both of us. So if anyone has like doubts like what should I cover, like more problems, some tough problems or some theoretical concept which are not clear, like let's discuss like what should be the how it should be going those lectures. Okay. I also shared my mail ID, like if anyone has any doubts please mail me and I will try to incorporate these in the all these in the next next week. We'll try to answer all your queries and all. So if besides this, if anyone has any suggestion and all, or any doubt regarding the recordings and anything else? Okay, then let's. If no one has any doubts, so please mail me if you feel any doubts regarding regarding any problem or all. So the next week will be a dedicated lecture focused on the week 2, and some more problems will be involved in it. So then, good evening, and then let's meet the next week. Thank you.